Hello everyone, and thanks for tuning in today. My name is Kim Flanagan, and I'm a technical support engineer for Indium Corporation. And today we're going to talk about the basics of reflow soldering from a solder manufacturer's perspective. We'll start off today by talking about the basics. We'll start off learning a little bit about the reflow process. Then we'll talk about the material so that we can later on understand how the material interacts with the reflow process. We'll understand the differences between lead and lead-free solders and the substrate metallizations and how intermetallic growth occurs so that later on we can fully understand how the reflow process affects the intermetallic growth. We'll move into talking about reflow profiling, what each stage of the reflow profile does to the quality of the solder joint, and some best practices for reflow profiling. And then we'll spend a good chunk of our time talking about some solder defects related to the reflow process and how to troubleshoot them. When we talk about troubleshooting solder reflow defects, it should be noted that it's important to define the root cause of the issue before trying to troubleshoot the issue. There can be one solder defect that has many different root causes, which can lead to different troubleshooting methods. Same thing goes for troubleshooting. There can be many different ways to troubleshoot one root cause. And today we're going to talk about troubleshooting from the reflow process side of things. Understanding the reflow basics. For a standard surface mount technology reflow convection oven, there are essentially 4 different important aspects to consider: the zone temperatures, the belt speed, the overall length of the oven, and the atmosphere, whether or not you're reflowing in just air or if you have a nitrogen purged oven. A little bit more about some reflow basics. A reflow profile is a chart that defines the reflow steps, or the heating steps of an assembly during the reflow process. There are 4 main different types of reflow profiles. There's a ramp to peak profile, which is just a linear profile similar to the one in the blue in the picture below. There's a ramp soak spike profile, which is the black line in the bottom chart, where the profile starts off linear, but then it flattens out at a given temperature for a given amount of time, and then it spikes up to the peak temperature. There's a shoulder profile, which really is more like the linear profile pointed out in the picture below, where there's a small little soak just before the melting point of the solder. And then there's a plateau profile, which is a newer type of profile ideal for low temperature solders that require low processing temperatures and longer time above liquiduses. So in a profile, in any of these profiles, there are 6 different attributes that should be taken into consideration for having an ideal quality solder joint. You have the ramp up rate, which is essentially how fast your assembly is heating up. You have the soak time, which is optional in a lot of profiles, where you hold your reflow temperature at a given range for a given amount of time. You have the peak temperature, which is the maximum temperature that your assembly sees. You have the time above liquidus, which is the amount of time that the solder is molten. You have the cool down rate, which is essentially the opposite of the ramp up rate. It's how fast or how slow the assembly cools down, which will affect the microstructure of your solder joint. And then you've got the time from ambient to peak. Ambient being usually about 25, 23 degrees Celsius, whatever room temperature is, all the way up to your peak temperature. How long does it take to get from point A to point B? Moving into the basics of the materials, let's talk about the solder paste. Solder paste is made up of two ingredients, flux and solder alloy powder. These two ingredients are mixed together in about a 50% to 50% ratio by volume to make this almost looks like gray peanut butter. I joke around with people that it's gray peanut butter because essentially flux has a similar consistency to honey. And then when you add the alloy powder and it changes the color, you get gray peanut butter. Besides the flux and the powder, there are three other contributing factors to the solder paste. You have the particle size of the alloy powder. Standard particle size in the industry today is either a type 3 powder size or a type 4 powder size, but as the type number increases, the actual particle size decreases. You also have the metal load. How much alloy powder to flux ratio do you have? Typically, this is between 88% to 90% metal load because metal is more dense than flux. This value is given in terms of weight percent. And finally, the packaging. The packaging isn't often a major consideration. However, it does affect how the material is manufactured. Typically, if you order in a syringe for a dispense application, the metal load will decrease for the solder paste. This is to ensure that there is no tip clogging. If you order solder paste in a jar for stencil printing or in a cartridge, the metal load will be optimized for that process as well. So let's just talk about the flux chemistry. Essentially, the flux has a main purpose of removing surface oxides from not only your surface metallization, your PCB metallization or whatever you're soldering to, but also from removing surface oxides from the individual solder particles within the solder paste. It does this, you need to remove the oxide layer because it helps to promote wetting. It helps to make sure that the solder is wetting to your surface properly. The flux also provides an oxidative barrier, prevents further oxidation from occurring during the reflow step. It is also, as I mentioned previously, has the consistency of honey. So you can use it as a medium to suspend the solder powder particles and make it a homogeneous, smooth mixture, easily for processing. You want to make it easy for printability and easy for dispensability. You want to make sure that the solder bead on your stencil is rolling smoothly and is dispensing smoothly. And then one final comment about the flux chemistry, you don't want it to interrupt the thermal transfer efficiency. So it has to have minimal thermal resistance. There are essentially three different flux types. You have the most common flux type, no cleans, which the flux residue is benign after the reflow step. It does not pose any threat to electrical reliability or corrosion. You have RMA flux type, which is a rosin-based, mildly active flux. And you have water-soluble fluxes, which essentially are typically very aggressive fluxes, and the flux residue can just be removed with water wash. This chart here represents how prevalent each type of flux is in the industry. This chart here is a little old, so there might be some slight variation. However, it kind of gets the picture across that most common solder paste purchased nowadays are no cleans. In the flux, you have 4 different groups of chemicals that go into a flux recipe. You have the activators, then there's rosin, rheological additives, and solvents. And today we're just going to talk about the no clean fluxes, although water-soluble fluxes are also very common. In this example here, we're just going to talk about no cleans and even some RMAs. The first set of chemicals are the activators, and historically only one activator chemical was used. Today, there are typically multiple activators combined together to create an activator package. The function of these activators are to remove the oxides from the metal surface. They're the chemicals that are doing the work to ensure solderability. So they remove the oxides to promote wetting. And they're typically halogenated compounds or organic acids that dissolve the surface oxides. The activators affect the paste shelf life and also the electrical reliability. The paste shelf life is dictated by the activator shelf life because over time, the activators will expire and no longer do what they're supposed to do to remove oxides and promote wetting. For electrical reliability, because they are halogenated compounds or organic acids, they could pose threat to electrical reliability. So rosin, the second group of chemicals, is used to encapsulate those activators and keep the flux residue benign. Rosin is exactly tree sap. Then you have resins, which is synthetic rosin. Rosins and resins are not used in water-soluble fluxes, which is why we're only talking about no-clean and RMA fluxes today. Rosins are tacky and viscous, and as I mentioned, they encapsulate any harmful chemicals that can pose threat to electrical reliability. They make the flux residue benign. They act as an oxidative barrier during the reflow step, and typically they're medium to high molecular compounds. The third group of chemicals in a flux chemistry are the rheological additives. These are thixotropic gel compounds that affect the viscosity and rheology of the solder paste. They make it so that the solder paste has the ability to flow well, roll well on the stencil, and are slump resistant. And then finally, the last group of chemicals are the solvents. The solvents are chemicals that homogenize the flux. They dissolve the activators and rheological additives and rosins, and they make a uniform paste mixture. The solvents are key in voiding, and they do affect the viscosity, tack life, and shelf life of the flux. Moving forward with talking about the alloys, the two most common solder alloys in the industry are SN63, that's a short name for an alloy that has 63% tin and 37% lead, and the lead-free alternative, which is commonly known as SAC305. This has a composition of 96.5% tin, 3% silver, and 0.5% copper. SN63 for many, many years was the go-to solder alloy. It has excellent reliability. It's eutectic, which means that it has a liquidus and solidus that are equal. It melts and solidifies all at the same temperature, in this case 183 degrees Celsius. It has excellent wetting and coalescence, very shiny solder joints. However, as the industry is moving towards lead-free, we are no longer allowed to use SN63 in many applications. The Restriction of Hazardous Substances Committee has deemed that lead is a toxic chemical that should not be used. For this reason, lead-free alternatives have entered the industry. SAC305 is not eutectic. It does have a solidus of 217 degrees Celsius and a liquidus of 220 degrees Celsius, giving it a plastic range of 3 degrees. It is a great alloy, however, not as reliable as the tin lead alternative. For this reason, many of us in the industry are working on other lead-free, high reliability alloys. Because the industry is moving towards lead-free, there tend to be more variety of flux formulations that are being developed. As of the past couple of years, recently, lead-free has surpassed the amount of electronics assembly than SN63 or any tin lead combination, because it is RoHS compliant. And so to end on a note about how the alloy affects the flux and hold the solder paste, let's understand the difference between the two flux vehicles for leaded and lead-free solders. Because tin lead solder has a lower melting point than SAC 305, typically the tin lead flux vehicles cannot handle higher temperatures. They typically don't need to. In a lead-free flux vehicle, they're designed for lead-free alloys, which means that the excessive lead oxide that forms on lead cannot always be compatible with the chemistry designed for lead-free. In many cases, however, there are flux vehicles that work for both leaded and lead-free solders. You'll have to ask your solder supplier if that is an option. A necessary evil, intermetallics. Intermetallics form between the solder and the component and the board. Intermetallics are when the solder dissolves the substrate metallization or the component metallization and forms a mechanical bond with each the component and the board. As you can see where the two red arrows are pointing, there are two intermetallics. This is a cross-section image, cross-section scanning electron microscope image of a solder joint with an intermetallic formed on the component, which is on the right side here. I'll point with my arrow. This is the component, and here's the intermetallic, and then here's the solder joint. Then on the bottom here, you've got your PCB, and then this little white line is the intermetallic between the solder joint and the board. I say that they're a necessary evil because they're necessary for a mechanical and electrical bond between the component and the board, or the solder and the board, or the solder and the component. And the reason why I say evil is because that is at the intermetallic boundary, that is where typical failures usually occur, because the intermetallic is the most brittle part of a solder joint. As I mentioned previously, the intermetallics form a mechanical and an electrical connection. They're typically tin-rich, and the reason for that is because tin in solder alloys is actually the element that dissolves your substrate metallization and forms the intermetallic. In the bottom picture here, you can see a micrograph of an electron dispersion spectroscopy of the intermetallic that we previously saw. It has mostly tin in it. Intermetallics are typically 1 to 5 micron in thickness. However, they can be less and they can be greater. However, for mechanical reliability purposes, you do not want to exceed 5 microns thickness, and you don't really want to go below 1 micron thickness. In copper metallizations, which we'll talk about in the next slide here, the difference in dissolution rates, you'll have different thicknesses of intermetallics compared to nickel. As we mentioned earlier, intermetallics are the most brittle part of the solder joint. So as your intermetallic thickness increases beyond 5 microns, your mechanical reliability may be compromised. If you are below 1 micron thickness, your mechanical reliability may also be compromised due to not enough strength holding the solder joint to the assembly. And intermetallics depend on 3 things: the temperature of which you're soldering or which the solder is seeing, the amount of time that the solder is exposed to the temperature, and also the dissolution rate between the 2 elements. As you can see in this picture here, using a solder and soldering to copper at 700 degrees Fahrenheit, the dissolution rate between the tin and the copper is 61.5 microinches per second. At that same temperature with that same solder, nickel has a dissolution rate of 1.7 microinches per second. For this reason, you can typically see thinner intermetallic thicknesses with nickel substrates versus copper substrates. So let's get back to reflowing. There are essentially four main stages to a reflow profile. The first stage is the ramp-up stage. At this point, the flux in the solder paste is drying out. The solvents are evaporating and preparing the activators for oxide removal and then for wetting. The activation stage, this is where your activators in the flux chemistry start to remove the oxides and prepare the surfaces of the metallizations for wetting. At the time above liquidus, the solder starts to melt and starts to wet and form intermetallics. The cool down rate affects the microstructure of the solder joint. A fast cool down rate will create a tiny microstructure, which makes a stronger solder joint. A slow cool down rate will create a larger grain structure, which makes the alloy softer. However, assemblies can't handle too fast of a cool down rate because of CTE mismatch. You have different materials in your assembly that expand and contract at different rates, and that can pose stress and strain on the solder joint and cause it to fracture or break. So it's a balancing act. Reflow profiling. We started to talk about reflow profiling in the beginning of the presentation. Reflow profiling is when you hook up thermocouples to your assembly to read the temperatures that the solder joint is seeing during the reflow process. The reason why I have a picture of a turkey up in the corner, which you were probably wondering about in the beginning, is because if you think about a turkey, a 10-pound turkey, let's say, you can set your oven to 350 degrees Fahrenheit, but the turkey isn't going to read 350 degrees until 3, 4, 5 hours later. And that amount of time and that amount of temperature is going to depend on how large the turkey is, because there are different thermal masses. The same concept applies to a circuit board. For every assembly, a different profile should be conducted. And the reason for this is because every assembly has a different thermal mass. The board's thermal mass, the component's thermal mass, the component density on the board. Each assembly is unique and different and deserves its own reflow profile. So for attaching the thermocouples to the assembly, you may want to attach them with the best practice method, which is to solder them with a high temperature solder. You want whatever your attachment method is going to be thermally conductive so that the temperature readings are more accurate. If you don't have access to a high temperature solder, many others use conductive epoxies or aluminum tape. In the picture down below, I've used aluminum tape, which is the white tape on the bottom attaching the thermocouple tip to the board. And what you'll also see on this picture is Kapton tape. And Kapton tape is not a good method for attaching the thermocouples to the board. And the reason for that is because Kapton is actually an insulator. So it will affect your results and not give you an accurate temperature reading if you cover the tip of the thermocouple with the Kapton tape. What I do use the Kapton tape for is to secure the wires of the thermocouples down to the board so that they don't get hung up in the oven. I'll also use Kapton tape to window pane around the aluminum tape if I'm using aluminum tape. The aluminum tape could pop up after multiple reflow cycles. So Kapton tape secures the aluminum tape down a little more so that the aluminum tape doesn't pop up during the reflow step. Be careful that the Kapton tape does not cover the tip of the thermocouple where the reading is being measured. It's important to attach the thermocouples directly to the solder joint. In the image here, you'll notice that I have one thermocouple attached to the QFP. In many cases, or in certain cases, I should say, you may want to know what temperature the component might be exposed to if it's a temperature-sensitive component. This is an instance where you may want to attach a thermocouple to the top of the component. And the same thing goes for the board. However, if you're reflow profiling for the purpose of optimizing the solder joint, then you're going to want to make sure that the thermocouple is attached to the solder joint itself. I've actually run a DOE where the thermocouple was attached to the top of a component and the thermocouple was soldered under the bottom of the component. And there was a 10-degree difference between the two readings. So it's important to make sure that the thermocouples are attached to the solder joint. For bottom termination components, this may seem difficult. However, it's important that you drill underneath your PCB to access the solder joint underneath the component. From there, you can attach the thermocouple through the board to the solder joint, and you'll get a more accurate reading. The locations of the thermocouples are important to consider. For higher component density boards, unlike the one in the picture, you can have a lot of small components, you can have a lot of large components, and they can be mixed all over the board. What you'll notice is that larger components, because they have higher thermal mass than smaller components, will typically take in more heat and read at cooler temperatures. For smaller components, the opposite is true. They have less thermal mass, so they tend to get hotter. They tend to read hotter temperatures. So you may, if you're profiling a new assembly, make sure to attach thermocouples to the larger components on your board as well as the smaller components on your board. Also, around the edges of the board typically read higher because they're not surrounded by as much thermal mass compared to the center of the board. The center of the board is surrounded by more thermal mass, so they typically read cooler temperatures. And finally, if you're having any kind of issues with particular components that you're trying to troubleshoot, it's important to attach the thermocouple directly to that component so you can see exactly what that temperature reading is for that solder joint. And finally, the most important consideration for profiling, profile with a populated board. I can't tell you how many times I see people profiling with a bare board and it will not give you an accurate reading. I promise you, you will see a major difference between a bare board and a populated board. I know that not all components are cheap. I know not all boards are cheap. Dummy components are available, but it will be absolutely worth it in the long run and in the quality of the solder joint or quality of the whole assembly in general if you profile with the populated board and get accurate readings. If you're a contract manufacturer, make sure that your customer understands the importance of profiling with a populated board and how it's going to affect the overall quality of the product that they're getting. Some common solder defects that are often seen and how to troubleshoot them with the reflow step. As I mentioned earlier, it is important to understand that when troubleshooting solder defects, you must define the root cause of the defect before being able to troubleshoot it. And as I also mentioned, there could be many different root causes or many different ways to troubleshoot. In this case, we're going to troubleshoot using methods from the reflow step. The first common solder defect is voiding. We hear a lot about voiding. Voiding occurs because the flux in the solder paste is outgassing and evaporating during the reflow process, and when the solder powder starts to melt, that flux can outgas into the solder joint and form voids. What you don't want to do for profiling for voiding, in the case of voiding, is have a ramp up rate that is too fast. What this can do is it could disallow the flux to outgas. It won't give it enough time to outgas before the solder becomes molten, before it surpasses the liquidus. Also, if you ramp up too fast, the paste could slump, which will decrease the standoff height. And this is especially important for bottom termination components because the flux is already having a difficult time trying to outgas and escape from underneath the body of the component. As you reduce that standoff height, it becomes even more difficult for the flux to escape and has nowhere to go, so it forms more voids. So as the paste slumps, it reduces the standoff height and creates more voiding. However, if the profile is too short, from the ambient temperature to the peak temperature, you're not allowing enough time for the alloy to wet to the surface. And you can get some inconsistent outgassing as well. If you have too low of a peak temperature, it could also reduce the wetting of the surface. And what happens when you reduce the wetting of the surface is that the solder alloy is not wetting and it's not pushing away the flux volatiles that are evaporating. In this instance, the volatiles will stay under the component or in the solder joint and form voids. And finally, if you have too high of a peak temperature or too long of a profile length, you could get excessive oxidation on your surfaces. This will also cause some non-wetting areas where the flux will outgas to. It'll blow up like a balloon and you'll have a void. You could also exhaust the flux. When you exhaust the flux runs out of activation power and will lead to oxidation issues. Also, if you have too high of a peak temperature or too long of a profile length, there could be many other reflow defects that could happen that we can cover later in the next few slides. Poor wetting. We talked about poor wetting a little bit in the beginning, in the last slide. Poor wetting is when the solder doesn't properly adhere to the substrate or the component during the reflow process, and it doesn't maintain its shape or size of the original deposit. This can cause problems for intermetallic growth or mechanical reliability. So some causes of poor wetting, as we mentioned in the last slide: oxidation of your surface finish on the PCB or oxidation on your component. The flux activity level not being strong enough to properly remove oxides. Too much heat input prior to the solder melting, which will cause more oxide formation, thus more chances for non-wetting to occur. And then finally, contamination, fingerprints, lotions, or anything that you would consider contamination. Some ways that you could use the reflow step to promote wetting is to use a ramp profile, a straight ramp to peak profile, or minimize the soak zone in the profile to minimize the overall heat input to the assembly. Also, ensure that the components are stored in a cool, dry place that minimizes oxide formation, because as the components and the board go through the reflow step, Oxidation will be more difficult to remove if it's got a higher initial oxidation rate. Graping. Graping is a solder defect that essentially happens because as paste deposits get smaller and smaller and the heat from the reflow step starts to affect it greater than for larger paste deposits because of the smaller thermal mass, the particles in the solder paste oxidize and they do not coalesce very well. This is also more common as particle size in the solder paste becomes smaller and smaller. As you decrease the particle size, there is a higher relative surface area of exposed solder particles compared to a larger particle size. This gives more of a chance for oxidation to form on the outside surfaces of the finer particles. Graping usually occurs at higher temperature or longer profiles, especially ones that are required for lead-free soldering, where the melting temperature of the alloy is higher, thus the reflow profile is typically hotter. How to reduce graping is by minimizing the soak or the plateau in your profile and reducing the overall heat input. Minimize the peak temperature while also taking into consideration the solder paste manufacturer's recommendation on the data sheet for a profile. And make sure that your assembly is going through a reflow profile that is generally about 4 to 5 minutes long. Any longer than that, you could be exhausting the flux and allowing those solder particles to oxidize. And finally, you can also eliminate graping with a solder paste flux choice, such as a more thermally stable flux vehicle or a more aggressive flux vehicle. And I would just like to note that many instances where I troubleshoot graping issues for my customers, it is often misunderstood for what is called cold solder, where cold solder is when you are not reflowing the solder at a hot enough temperature and the particles do not melt, but rather they oxidize and do not coalesce. It looks very similar to graping, but they have two different root causes. The root cause for cold solder is not giving enough heat input, but the root cause for graping is too much heat input. So make sure you're understanding the difference between graping and cold solder. And the way to determine this is by hooking up some thermocouples to that solder joint and reading the temperature. If it's above 220 degrees Celsius for SAC 305, the solder is melting. If it's below that, it's not melting. And the only way to know that is by hooking up a thermocouple and profiling. Some other defects that are caused by high peak temperatures. Charring of the flux residue, where the flux residue essentially looks burnt on the assembly. And the reason for this is because the peak temperature is too high or there's too much time above the liquidus of the solder alloy. De-wetting, which is different than non-wetting, is when there's uneven wetting across the pad because there's too much heat input. The solder starts to retract away from the solder fillet or the full wetting. The reason for this is there is excessive oxide formation caused from too much heat input. And finally, excessive intermetallic formation. If you have too hot of a peak temperature, you can get too thick of an intermetallic, which can cause some mechanical reliability issues down the road because, as we mentioned before, intermetallics are the most brittle part of a solder joint. However, they're necessary. Hot slump and bridging. Some of the causes of hot slump relate to the viscosity of the solder paste. As the viscosity drops during the reflow step with increased temperature, the paste could slump, and this could risk bridging 2 solder joints or more in the reflow step. Some ways that you could eliminate hot slump and bridging is by slowing the ramp rate of your profile and allowing gradual evaporation of the solvents and chemicals in the flux. There are also many ways to eliminate hot slump and bridging in the printing step, such as modifying the aperture design. However, today we're only talking about the reflow step. Tombstoning and skewing. I love talking about tombstoning. It is a very simple fix with the reflow step. What a tombstone is when you have a chip component, like a resistor or a capacitor, that is sitting on 2 solder paste deposits. And as the assembly is going through reflow, the 2 different solder paste deposits may see 2 different temperatures at 2 different times. One solder joint can start to melt faster than the other. The solder deposit that melts faster than the other deposit will start to pull the component upwards due to surface tension, and it will form a tombstone. Sometimes the component will even rest back down on the other solder joint, but will not coalesce or form intermetallic bonding with the component in the solder joint. You could also get skewing, which is twisting of the component due to an imbalance of forces because of the differences in melting times of the 2 different solder joints. And also, if there's too much paste printed on the 2 pads and as they melt or as they are reflowed, the solder paste deposits connect together underneath the component. One of the solder paste pads could pull away solder paste away from the other pad. When this happens, you have more solder on one pad versus the other pad. This will also create an imbalance of surface tension forces on the component, which can cause it to tombstone. Some strategies to eliminate tombstoning. You can add a soak to your profile to help get the cooler solder joint equal to the temperature of the hotter solder joint. You could slow down the ramp up rate of your profile to do the same thing, to make sure that the solder paste deposits are at the same temperature throughout the entire length of the profile. And here's an interesting one, turning off the nitrogen. If you are reflowing in a nitrogen atmosphere compared to an air atmosphere, it will promote faster wetting. When you're tackling tombstoning issues, you want to decrease the wetting speed. When you decrease the wetting speed, you allow there to be lesser of an imbalance of forces on the component. Again, when having nitrogen purged reflow ovens, it will increase the wetting speed, which will contribute to more tombstoning. In not all cases, but in many. So if you're having a tombstoning issue and you're using nitrogen, turn the nitrogen off. And then aside from the reflow process, there are printing and placement strategies to eliminate tombstoning as well. Also materials as well, which alloys. Typically, SN63 is more prone to tombstoning compared to lead-free alloys. And this is because it is a eutectic alloy. It melts and solidifies all at the same temperature. There's no plastic range, so the wetting is quicker. For alloys with a plastic range, like SAC 305 or other alloys that have a larger plastic range, the wetting speed is reduced. And this could help with any tombstoning issues. There are special alloys out there that soldering companies develop, particularly for tombstoning mitigation. Head and pillow versus non-wet opens. Sometimes the difference between the two is hard to determine because they're very similar. However, the root causes to each defect are very different. Head and pillow and non-wet open defects occur with BGAs. Head and pillow, essentially, is due to component warpage or board warpage during the preheat and soak profile. What happens is that when a component or board warps, the solder paste deposit and the BGA ball separate during the reflow step before they melt. Then, when the BGA ball and the solder paste start to melt, they coalesce separately and an oxide layer forms on the surface of each. When the assembly cools down, the component warps back to flat, or the board warps back to flat. And at that point, it's already too late for the solder paste deposit and the BGA ball to coalesce homogeneously. For non-wet opens, something similar happens. It is also due to component or PCB warpage. However, it is typically due to the pad of the PCB oxidizing too much or having too much oxidation, or not having a strong enough flux chemistry to remove the excessive oxidation. And the solder paste will attach to the BGA during the warping, and it will form a homogeneous solder mixture between the BGA ball and the solder paste. However, it will suck up all the solder paste from the pad, and then when the assembly flattens out as it cools down, there's no intermetallic connection between the BGA and the pad. Some solutions for this: you can reduce the heat input for your assembly. You can use a low temperature solder or low temperature profile. There are materials options that are designed specifically to tackle these challenges. They're typically tackier solder pastes, and then you can also use extra flux as well. But typically, head and pillow and non-wet open defects, the most common way that I see people reducing these defects is either a low temperature solder or using some extra flux. Could also contact the component manufacturer or the board manufacturer for their recommendations. Solder spattering. Solder spattering is when not all of the solvents have dried out during the preheat stage of the reflow profile. And what happens is, as the solder starts to melt, or as the temperature of the flux starts to heat up, it will spit and spatter some solder particles around the edge of the flux pool and all around the assembly. A way to reduce solder spattering is to slow down the ramp-up speed. And you can do this by either adjusting the belt speed of the convection oven. You can increase the delta between the zones of your oven, the delta being the difference between zone 1 and zone 2, or zone 3 and zone 4. And finally, you want to make sure that the first zone in the oven is no greater than 130 degrees Celsius, because that time from ambient temperature, which is about 25 degrees, to that first temperature is critical in ensuring that there's no solder spatter. Sometimes this is difficult if you're using a lead-free alloy, which has a higher melting temperature, and you only have a smaller oven, such as a 4 or 5 zone oven. But keep in mind that that first zone temperature is important for solder spattering. You can learn more about solder spattering from my colleague Leon Rao, who's going to be presenting on process optimization for reducing solder paste splatter during reflow. And last but not least, solder balls. Solder balls are often referred to as mid-chip solder balling. In the image to the right, you can see where the two paste deposits may have connected under the body of the component. And then as the solder starts to melt, surface tension separates the two, but leaves behind a little bit of solder under the component, which squishes out to the side of the component, creating a solder ball. In most cases, this is a printing or stencil related issue, which can be mitigated or remedied from modifications to the stencil or optimizing the printing process. So some causes to solder balling could be inadequate flux activity. You can have excessive oxidation that the flux cannot remove. You can have flux exhaustion from too hot or too long of a profile. You can have expired paste where the activators no longer remove the oxidation. And also slumping. When the assembly goes through the reflow step and possibly the component or the paste deposits slump under the component, as I mentioned, the two paste deposits can connect under the body of the component, and as they start to melt, surface tension will pull them back and separate them, but still leave some solder under the body of the component. Slumping can be caused by too much humidity exposure to the solder paste, too fast of a profile, or incorrect storage. I'll give you an example. As you have a jar of solder paste, you can open the jar of solder paste and use it. If you still have some solder paste left over in the jar and want to use it later on, what I see a lot of people wrongfully do is put the cap back on the solder and put it in the refrigerator for use for later. You don't want to do this because what happens is when you expose that solder paste, once you break that seal of the solder paste and you expose it to the environment, the humidity and the temperature, you put the cap back on it and you put it back into refrigeration, condensation can form inside the jar and water will mix in with the solder paste and cause some slumping issues later on down the line when you want to use more solder paste. If the root cause is slumping because you're incorrectly storing the solder paste, you can create solder balls. So a way to fix these challenges is to slow down the ramp-up rate or reduce the belt speed to dry out the solvents. Use a fresh slot or fresh jar of paste or reduce the amount of heat input so that the flux is not exhausted. And then again, as I mentioned, this is mostly a printing step issue, but there are other printing and placement solutions that can be considered as well. So I want to thank you all for joining today. And if you have any questions, my contact info is below, and you can email askus@indium.com or call our front desk number at 315-853-4900 to get in contact with one of our applications engineers. Thank you.